Good morning, dear students. Today we are going to discuss another topic from chapter Gravitation of class 11th Physics. The name of the topic is Kepler's laws of planetary motion. Kepler has given three laws to describe planetary motion and to explain planetary motion. And today we are going to discuss first law of Kepler given for planetary motion. This law is called law of orbits, and it states that each planet revolves around the sun in an elliptical orbit with the sun situated at one of the two foci. Foci is the plural of focus. Now in this diagram you can see this is an ellipse. A planet is revolving around the sun and sun is at one focus of the ellipse. There are two foci, one is at point S and the other one is at point S dash. So sun is at one focus which is point S, and there is center of ellipse also, right? Now there are two axes, one is PA which is called major axis and another one is BC which is called minor axis. Now to understand this particular law, we must understand first of all that what is ellipse, how is it related to circle, and when will we get ellipse. So let's draw two figures. One, let us say one is ellipse and the other one is circle. Now here beta, let this be the center of ellipse and this is center of circle. Now this portion is minor axis. Minor axis is given by 2b and this is major axis given by 2a. Then now if we draw these two lines and from the center if we see, then these two axes are further divided and are called semi-major axis and semi-minor axis. Semi-minor axis is B and semi-major axis is A. Now if we write the equation for our ellipse, then the equation for ellipse is x square upon a square plus y square by b square is equal to 1. And if we draw equation for circle, then the equation is x square plus y square is equal to a square. Now this b and a have a relation, and that relation is b is equal to a into 1 minus e, where this e is eccentricity. And this eccentricity decides whether we will get a circle or an ellipse and how much the ellipse will be pressed. How? Because eccentricity has value between 0 to 1. Now, if E is equal to 0 and we put this value in our equation, then we get B is equal to A into 1 minus 0. That means B is equal to A. So putting this value in equation of ellipse, we get x square upon a square plus y square upon a square is equal to 1, or we can say x square plus y square is equal to a square. So this is nothing, this is our equation of circle. So if E is equal to 0, then we get circle, and if E is between 0 to 1, then we get ellipse. And this E, if the value of E is increasing towards 1, then B will become smaller, right? So for ellipse, B is always smaller than A. Okay, so from here we understand that ellipse has equation x square upon a square plus y square upon b square is equal to 1, and b and a have a relation which is given by b is equal to a into 1 minus e. Here e is eccentricity. Eccentricity's value lies between 0 to 1. If e is equal to 0, then we get equation for circle. because here all the points at the circumference of the circle are equidistant from the center, whereas in case of ellipse the points at the circumference are not equidistant from the center. Okay, this is the basic difference. This is basic difference between ellipse and circle. Sorry, I had to stop because of the jet passing by. So now we understand what ellipse is. We have to understand what will be the coordinates of ellipse also. So let us draw another ellipse. And now let us understand different coordinates of ellipse. First of all, about these two axes, along y-axis we have b. So the value of coordinates will be 0, 2b, 0, minus 2b, and along x-axis if we say, then it will be 2a, 0, these points p and a, which I have shown you already, and here it will be minus 2a, 0, and this will be 2a, 0. And if we talk about the foci, so foci will have the coordinates a, e, 0 and minus a, e, 0 and a, e, 0. These will be the coordinates. It can be asked that what will be the coordinates for the foci. If the foci is at this coordinate, then it will be AE0, and if the foci is at the your second or third quadrant, then the value of the coordinates will be minus AE0 for x-axis, right? So these are the coordinates. You have to understand this. If sun is at this point, then this will be perihelion, closest distance, and this will be the aphelion, farthest distance. All these things you should be understood by you. Now we come to our law of orbits. So law of orbit simply says that each planet revolves around the sun in an elliptical orbit with the sun situated at one of the two foci. So here if we talk about this point, the sun is at focus S, then its coordinates will be AE minus AE 0. If we take sun to be at this point, then the coordinates will be AE 0, and this will be 0 minus 2b. This will be 0 plus 2b, and this is 0 minus 2b. This point P will have coordinate minus 2a 0, and A point will have coordinate 2a 0. Okay, now let us prove Kepler's first law. We take sun to be at this point, this focus, and we say let the planet be at point P. Now the planet is at position vector r with respect to sun, and due to gravitational force this planet is orbiting around the sun in elliptical orbit. So this force F is towards the sun, and the position vector r for planet P will be away from the sun. So here you can clearly see the directions of r and F, they are opposite to each other. And if we talk about the velocity with which the planet is moving, that is linear velocity, it is always given by the tangent drawn from the point. So this is showing, V is showing the linear velocity of the planet P. I hope you have understood this diagram. So I explain it once again. Sun is here. This is at one focus of the ellipse, and it is at a position vector r from the planet P. So sun is the origin, and P is having the position vector r with respect to sun. I have already explained to you what is a position vector. Then force F is being applied by sun on planet P. This force F is the gravitational force. Due to this gravitational force, the planet revolves around the sun in the elliptical orbit, and we know that this gravitational force is playing the role of centripetal force. This we have already discussed. Now The planetary motion takes place under the action of gravitational force exerted by the sun. So F is equal to minus G ms mp r upon r cube into r vector. What is ms here? Ms is the mass of sun. Small mp, this is mass of planet. Capital G is universal gravitational constant. R is the position vector of P with respect to sun. Now, this is the vector form of our gravitational force. So we have to show the direction also. So this negative sign is showing the direction of force which is opposite to the position vector. So this negative sign is indicating that F is opposite to the R, or F is oppositely directed to R. Now we know that the force is producing turning effect, so torque will come into play, and torque is given by the relation torque is equal to R cross F. That is, torque is cross product of the position vector and the force. Now putting the value of force here, we get R cross minus G ms mp upon R cube multiplied by R vector, and this is equal to 0. Why? Because r vector cross r vector, that is cross product of two vectors, equal vectors, will be 0. We know that they will be parallel to each other. The angle between them will be 0 degree. So r cross r is r sine theta. Sine theta, theta is 0. So sine 0 will be 0. So r cross r becomes 0. So torque, the rate of change of angular momentum, right? We know that torque is equal to rate of change of angular momentum. So it can be given by dl by dt. Now torque is equal to 0. That means dl by dt will also be equal to 0. So what does this mean? That dl by dt is equal to 0. This simply means that angular momentum is constant. So this shows that the angular momentum of the planet about the sun remains constant both in magnitude and direction. So when the planet is near to sun, then also the angular momentum will be same, and if the planet is away from the sun, still the angular momentum will be same. So every planet revolves around the sun in elliptical orbit, and the sun is situated at one of the two foci of the planet. Okay, so this is our proof of first law. Let me explain the derivation once again. What you have to basically prove to prove first law of planetary motion, we just have to prove that angular momentum for the planet remains constant. So let us start again. We have drawn this diagram. This is ellipse and sun is at one of the focus of the foci of the ellipse. Now we take a planet P which is at distance r from the sun. This r is the position vector r from the sun to the planet, and the planet is experiencing a force due to sun's mass, and that force is gravitational force. This force is playing the role of centripetal force, and the planet is revolving around the sun. Now this planetary motion takes place under the action of gravitational force exerted by the sun. So F is equal to minus G ms mp upon r cube into r vector, where ms is the mass of sun, mp is the mass of planet, r is the position vector. Now this minus sign is here because we are talking about the vector form. So this minus sign or negative sign is showing that force is opposite to the position vector. Now we know that if the planet is revolving around the sun, there will be some there should be a torque also, right? There should be a turning effect of force. Now let us see whether we are having a torque here or not. So torque is equal to r cross f, that is cross product of the position vector and force. Now putting the value of f here, we get minus g ms mp upon r cube into r vector. Now this is equal to 0 because the cross product between two equal vectors will be 0. So the torque becomes zero. That means no external force is being applied, or no external torque is being applied on the planet. So if torque is zero, no external force is being applied, then the rate of change of angular momentum will be equal to 0, because we know that if no external force is being applied, then according to Newton's second law of motion, the rate of change of angular momentum will be 0. So if rate of change of angular momentum is 0, that means that angular momentum is constant. So this all shows that angular momentum of a planet about the sun remains constant both in magnitude and direction. That means the planet revolves around the sun without any external torque being applied, and the angular momentum of the planet remains constant, right? So this is for today. I hope you like the lecture and you have understood all the points. Thank you and take care.